Okay, so we're back. I'm going to keep on going. So we just talked about some concavity stuff, and I want to, and I had mentioned that we're going to do a second derivative test that involves concavity. And I also mentioned that earlier we said a couple of different ways we could talk about whether something was a max or a min. Um, and I said that there was a third, more efficient way, and I'm able to show that to you now. So I'm going to cover both of those things off right now. So yeah, so recall, all right, do I have? Yeah, I do. Recall the following. Well, looking for max mins, right? So what we would do is, to find max mins or eligible max mins, we're going to do, we let f prime at x equal to 0 to find critical numbers. And then we could use, one way we could do is we could use the first derivative test, right? So after that, we would use the first derivative test. That's not a derivative. Wait a second. First that's terrible. Derivative test. And so what we would do is the first derivative test looks at increasing versus decreasing, right? So, if we, I had the wrong thing down. If we had this and then this, right? So we would have seen that f prime is greater than 0, and this one would be f prime is less than 0. And so then we know that, if this was a critical, right? So a critical number, we know that this guy would be a local max, right? Because it goes from increasing to horizontal to decreasing. By default, that guy's got to be a local max. The alternative is we could go from decreasing to increasing, and I don't really need to write the rest of the stuff down, but we know that this guy here, this guy is going to be a local min. And so that's what the first derivative test tells us, right? It tells us areas of increase, areas of decrease, and then, where the first derivative is equal to 0, that it's got a slope of 0, and a slope of 0, I want to just kind of revisit and remind, a slope of 0 can occur at a max, a slope of 0 can occur at a min, but there's also that weird potential case where a slope of 0 can occur at a point of inflection, right? So we've got a max, we've got a min, and we've got a POI, a point of inflection. So POI is no longer a point of intersection. When we're in calculus, more often than not, a POI is meaning a point of inflection. But if at any given time on an assessment or in class I say POI and you're not sure which I'm referring to, hit me up and I will absolutely clarify. This is still a lot of work, right? Like if you set f prime at x equal to 0 and you solve and you got your eligible critical values, not a ton of work by any means, but if I wanted to know whether it was a max or a min, it's a good idea. Like so it depends on our goal. If we're trying to do graphing, like if we're going to graph the function, first derivative test, you're going to do it, right? It's the first derivative test, and you are going to do it. So you're going to know whether they're maxes or mins. But if the objective was just to determine at a particular spot whether it was a max or a min, setting up a first derivative test is not necessarily ideal. But if you think about it, right, if it's going to be a max or a min, at that spot right there, right, it's got a slope of 0. So at this spot right here, we would have the f prime at x is equal to 0 because it's got a horizontal slope. But what's kind of cool, not only is f prime at x equal to 0, but in this case, you can see that this guy is concave down, right? So that would mean that f double prime at x would have to be less than 0 because it is a frowny, so it is concave down. So in fact, we wouldn't even really need to do a first derivative test. We could just evaluate what the second derivative is at that exact spot. And if the second derivative is less than 0, it means it's a frowny, it's got to be a max. If the second derivative is greater than 0, like this guy right here, we would know that it's going to be concave up. And so then that means that it is going to have to be a min. So by doing by evaluating the point in our second derivative, we only need to check one spot. We only need to actually check that exact spot. Now, this isn't perfect either, but it is still faster. So if the second derivative is equal to 0, it's probably, so f double prime is equal to 0, it probably is a point of inflection, but not always, right? And so, cast your mind back to that y equals x to the fourth example, right? This is a local min, right? So it's a local min. But if this was f double prime at x equals 0, you might think, oh, it's got to then be a point of inflection. But we know that it's a local min, right? So, so y equals x to the fourth. It's not the only function in the world by any means that satisfies this, but it's the easiest one. So it's not always a sure thing. And then you might say, well, how would I know then that it's a local max or min? Well, then you'd actually have to do the first derivative test, right? So the first derivative test is always going to be conclusive, right? Like this is kind of the gold standard of finding your maxes and your mins. But if you just want to, relatively quickly discern whether a point is a max or a min or not, you can do the second derivative and evaluate it. And most often you're going to find that it's the max or a min according to the second derivative. But if the second derivative is also 0, it's still not conclusive, and then you're going to have to actually do the first derivative test fully. But more often than not, you can tell whether something is a max or a min simply by examining the second derivative at that spot, okay? But now, okay, so the first derivative test tells us, areas of increase and decrease, and also it finds maxes and mins. Okay, so that's what the first derivative test does. It is the gold standard of that. You don't improve upon it. It's not always the most efficient, but it is conclusive, right? So then let's think about the second derivative test. So the second derivative test right? So we got the second derivative test, and we'll actually examine what a sign chart looks like for this in a minute. But we're going to take along the tops of our t's, right? Oh, that's the button over here. So if we're looking, what we're going to do is we're going to take where f double prime at x equals 0 and find critical values here. And so find criticals, and we're going to call them just x equals c. So maybe this is critical 1 and this is critical 2. And then we're going to look at the concavity on either side, right? So if f double prime at x is like negative, you're like, oh, that's means it's concave down in that area. And if f double prime is positive, oh, we know that that is concave up. And where the concavity changes, because if we go from concave down to concave up, we would know that, hey, that's a point of inflection. Whereas if this one continued, I mean, maybe we check over here and it's still concave up, then this is, it's going to be kind of another one of those of more testing or thought is required, right? But it's not, but what it isn't going to be, it is not a POI, right? And so that's going to be our second derivative test, is going to be putting the critical values from f double prime at x equal to 0 along the top. Also, so not only where f double prime at x equals 0 and vertical asymptotes, because if you think about a vertical asymptote, you can change concavity on either side of a vertical asymptote, right? So kind of think about a function that looked like this. So maybe we've got a vertical asymptote there. We could have a function that went like this, right? So on the left side of this vertical asymptote, I'm thinking about it for a second, is that concave up or down? It's up, right? On this side of the vertical asymptote, it could look like that, right? And this guy is concave down. So we want to have not only critical values, but we also want to, along the tops of our second derivative test, include vertical asymptotes, because again, the tops of our table of values in our sign chart they're the places where it's eligible to transition from one state to another. And certainly on either side of a critical value, it's eligible to happen, but also on either side of a vertical asymptote, right? So our second, and so that's true. I've mentioned this before. We haven't really examined it very much, but the first derivative test along the tops, we want to have where f prime at x is equal to 0 and vertical asymptotes as well. So vertical asymptotes are always going to be included in our sign charts, always, okay? So awesome. So let's continue on. So let's look at a super basic example. How about if we look at, and we've sort of examined this one already, but I kind of want to formalize it. Let's look at f at x is equal to x to the fourth. Now, we've talked about it. We kind of know what it looks like, but I want to see how all of this stuff bears out. So, you know, when we are sketching these things, we're always going to need f prime at x, and we're always going to need f double prime at x, right? So it's going to be 4x cubed, and f double prime at x is going to be equal to 12x squared. Lovely. So I'm going to, you know, for the sake of the first derivative test, I'm going to let f prime at x equals 0 to find eligible max mins, right? And when I do that, I think that you can pretty quickly discern that x equals 0 is what it's going to be. So let's do our actual first derivative test. Derivative test. And so, right, so and we only have one. There's no vertical asymptotes, but what we do have is, you know, a value, and it's going to be 0. So this is going to be from negative infinity to 0, and from 0 to infinity. So that's our domain. Grab a test value. So a test value like -1 and 1. And then list our factors. Well, there's only one. It's 4x cubed. And so that's going to be negative, right? And then so the result of that means that it is, because it's negative, it is decreasing. And over here, it's going to be positive. And so the result of that means that it is increasing. So what that tells us is that, okay, the point 0, comma, and you're going to put the 0 back into the original function. So I could say f at 0, which really is just going to be 0, 0, is because it's decreasing into horizontal into increasing, we can know that it is a, that's not how you spell local, that is a local min, right? So we have a local min at that spot. Right, and so then let's look at our second derivative test. I can pop back up to the top of the page here, or maybe we'll just try and squeeze it in here. Let's just try and squeeze it in here. So the second derivative test, so we're going to let f double prime at x equals 0 to find criticals, or really what they are is, we're really in general here looking for eligible POIs, right, is what really is going on here. And so, you know, in this case, it would be 0 equals 12x squared, and that just means, again, that x is going to be equal to 0. So it's a pretty boring sign chart for this guy as well. So here we go. So this is our second derivative test, and my apologies that this is as kind of garbagey as what it is, but I'm just kind of going quickly. So put a 0 there, same domain, right? So negative infinity to 0, and from 0 to infinity, that's going to be my domain. And then test value, again, I'm just going to go -1 and 1. And then the function I'm going to be testing here is 12x squared. And then we're going to have our result. And so this is going to be where it's going to look a little bit different. So this guy is going to be positive, right? So because it's positive, we're happy, or it's concave up. And over here, because it's squared, it's also positive, which means it is going to be happy, concave up. And so what we have is the concavity didn't change, so we can tell, therefore, it is not a point of inflection. And we knew that from the first derivative test. We knew that it was a local min. But that's what the second derivative test looks like, is we're going to test those values like that. Lovely, lovely, lovely. So I think that's all I want to cover today. So what I'll do is I will list out your homework. Actually, I'll put homework on Google Classroom. So there we go. Thank you, everybody. Hope it goes well. Have a lovely